talking about SQL tuning today. Kelly runs a blog by name tuningsql.com. He's also a very frequent speaker in several Oracle forums. We're very glad to have him here along with us today. I will hand it over to Kelly to introduce himself a little bit more, and then we'll continue with the session. If there are any questions, you could post it in the chat. And once the session is over, which is about in 45 minutes or so, then we will take up the questions and handle that as it comes. Over to you, Kelly.
All right, fantastic. So how do I go about sharing my screen?
There.
If you're talking, I think you might be muted. I'm sorry, I can't hear you.
Yeah, there's a share screen at the bottom. You should have that option.
Oh, tech
You
issue.
see the at the bottom there are participants, chat,
Share screen. There it is. Okay, I found it.
right.
Okay, is everybody able to see the screen all right? You see SQL tuning, undocumented secrets?
Yes, we can.
Okay, fantastic. So my name's Kaylee Crum. I write the SQL tuning blog. I'm an author, entrepreneur, Oracle Ace, OCP certified, all that jazz. But you guys came here to learn about this stuff. So let's get started. Let's talk about SQL tuning, undocumented secrets for getting accurate cardinalities. The first thing that we actually want to talk about is the word undocumented. A lot of people look at the word undocumented, they say, okay, so what? That just means it doesn't show up in the documentation, right? And that is what it means. But it also means something else. It carries a little additional weight with it. Number one, it means it's not supported by Oracle support. So if you run into difficulties with what I'm about to show you and you go crying to Oracle support, you go, oh, please help me with this. They're going to be like, sorry, can't help you. This is not a supported feature. The second thing that it means is it can be changed or revoked in any future release without warning. And this has happened before. Take, for example, before we had the function listag that was released in 11.204, there was a function that did something similar called wmconcat. People were using this before listag came around. Well, it was an undocumented function. And so people upgraded their database. Eventually, they came to 12.1, and wmconcat went away. And people were like, okay, Oracle, what happened to wmconcat? And they're like, well, you shouldn't have been using that. That was an undocumented function. So bear in mind that this can change at any point in time. Oracle support's not going to help you with it. So please don't use what I'm about to show you in production. Now, a lot of people are going, now, hold on, Kaylee, hold on. I came to this presentation for you to teach me how to use something. And the very first thing that you're saying is, don't use it. And that's not what I'm saying at all. What I'm about to show you is an extremely valuable tool that you can use to get the best possible execution plan. But it would be a very bad idea to use these undocumented hints in a direct way. Let me show you what I'm talking about. It would be a great idea to get the perfect plan using these undocumented fixes, but then use a documented method to enforce the plan, such as a baseline or a SQL patch, documented hints, etc. It would be a bad idea to get the right plan using these undocumented fixes and then use these undocumented fixes verbatim in your production code. So let's talk about cardinality for just a second. Cardinality is the number of rows that Oracle expects to return from a particular step in an explain plan or an execution plan. So whenever you're looking at a plan, you've got a column called rows. That's what we're talking about when we say cardinality in this case. Cardinality drives everything about your plan. It drives your table join methods, whether you're going to be using nested loops, hash joins, sort merge joins, merge join Cartesians. It drives your access paths, whether you're going to be using indexes, how you're going to be using those indexes, and if you're going to be doing a full table scan and avoiding indexes entirely. It drives your join order. And for those of you that have messed with SQL tuning, you know that your join order is paramount to getting a very good execution plan. So the problem is that Oracle's cost-based optimizer works with cardinality estimates whenever it's creating a plan. And whenever these estimates become inaccurate, if Oracle miscalculates the number of expected rows, the more inaccurate your estimate is, the more likely that the cost-based optimizer is going to do something inefficient, undesirable, slow. The more likely it's going to do something stupid. So let's talk about certain things in your SQL that can ruin your cardinality estimates. Let's talk about like and leading wildcards. Some of you might be familiar with the song Bottles of Beer. It's a song that goes 99 bottles of beer on the wall, 99 bottles of beer. You take one down, you toss it around, 98 bottles of beer on the wall, 98 bottles of beer. You keep on going all the way down until you get to no more bottles of beer on the wall, no more bottles of beer. Go to the store, buy some more, 99 bottles. There's 100 verses to this song. Let's say that we have a table called Bottles of Beer Song, and it's got 100 rows. And in each row, we've just got one column. We've got a song lyric column, and each row contains a verse of this song. So the question is, if I were to ask you, how many rows in this table contain the word beer? The answer would be all of them. All of these rows contain beer. But what if we ask Oracle? What if we say, hey, Oracle, how many of these rows contain beer? Let's say we do explain plan for select star. Ooh, little feedback there. Select star from Bottles of Beer Song, where the song lyric is like %, beer, %. And if we get the plan back using select star from table dbms xplan.display, you can see that Oracle thinks that there's going to be a grand total of 5 rows. What the heck, Oracle? We just said that there are going to be 100 rows, but Oracle thinks that there's only going to be 5. All right. Well, how many of these verses contain the word hippopotamus? Answer is none. Answer is 0. Big fat nothing, right? There's no hippopotamus mentioned anywhere in this song. But if we do explain plan 4, select star from Bottles of Beer Song, where the song lyric is like hippopotamus, if we pull that back and using dbmsxplan.display, Oracle again thinks that there's going to be 5 rows here. But again, hippopotamus wasn't mentioned anywhere in the song. So how does Oracle miscalculate this? Oracle uses statistics to come up with its cardinality estimates. Let's look at some of the statistics that Oracle records about tables and columns. First, we have table level statistics. These are statistics regarding things that are across the entire table. So that's going to be things like the number of rows in the table, the number of blocks that the table occupies, the average row length of a table. And so those are table level statistics. We also have column level statistics that are going to be recorded for each column in the table. And so this is going to record things such as the number of distinct values in a column, the high value of the column, the low value of the column, the number of nulls in a column, the density of a column, which is kind of like 1 divided by the number of distinct values, unless you have a histogram and then things get weird. The average column length. So the question is, we've got all these statistics to choose from. Which one of these statistics can help you accurately assess how many records are going to match the wildcard %, beer, %? Answer is none. None of those are going to help you. So the question is, how does Oracle arrive at a cardinality of 5? Anytime you have a leading wildcard, you say where column name like % something or column name like _ something, Oracle automatically just guesses 5%, just arbitrarily. You can picture what the Oracle developers were doing at this point in time. They were coding along and they're like, okay, what do you want to do whenever we come to this scenario? You want to just guess? Okay, let's just guess. What do you want to guess? 5? Okay, I like the number 5. Yeah, let's do 5. Okay. So it's just an arbitrary guess. So if we were to write a query like this, select star from Bottles of Beer Song, where the song lyric is like %, beer, %, and song lyric is like hippopotamus, Oracle is going to guess 5% of another 5%, or 0.25% every time. So how do we fix something like this? Well, we can use an undocumented hint called the opt estimate hint. It's very simple to use. You simply type opt_estimate, you open a parentheses, and you say table. Now, this is not a placeholder. This is literally, you type out table. You type out the keyword table, comma, and then you put a placeholder. Now, my table is going to change from your query. It's going to be either the name of the table that you're using or the table alias that you're using. And you put comma, you say rows equals however many rows you want the optimizer to expect. So once the optimizer knows how many rows to expect, once it has a corrected version of cardinality, then it's going to be able to come up with the best possible plan. So here's an example of us using the hint. We say explain plan 4, select. Anytime you have a hint, it has to be the first thing that's opened up right after your select phrase. You do a slash, you open a comment, you do a plus, you say opt_estimate, open parentheses, there's our table, comma, I say Bob's because that's our table alias is Bob's, and I say Oracle, I want you to expect 100 rows from this operation. And so whenever we do this, we get the plan back using dbmsxplan.display. Oracle now thinks there's going to be 100 rows. So the first thing you might look at whenever you see this hint, you say, wait a second, we're using the keyword table. That means it doesn't work for indexes, right? You'd be forgiven for thinking that because it sure looks like it would be that case, but this actually works with index fast full scans as well. And that's where Oracle reads an index instead of reading the table. So if we create an index called Bob's_IDX on our bottles of beer song table with our song lyric, and then we do the same plan, suddenly we get an index fast full scan, and Oracle is still expecting 100 rows. So it's okay to use with index fast full scans as well. Let's take another example. Let's try a create or replace view. We're just going to make a view and call it lyrics containing beer. And we'll say as select star from bottles of beer song, where the song lyric is like %, beer, %. So we've got our view in place. We're only selecting lyrics that contain the word beer, which is all of them in this case. And if we do explain plan 4, select star from our view that we just created here, you can see when we get this back that we're expecting 5 rows. Okay, we didn't use any hints. Let's use a hint now. Explain plan 4, select, and then we open up a hint. Opt estimate, table, comma, Bob's, comma, rows equals 100. Now when we use this hint, nothing changed. We still have 5 rows. What the heck happened? Why is Oracle ignoring our hint? Fun fact for you, Oracle doesn't ignore hints. Hints are actually directives, and if they are valid, Oracle will follow them. If Oracle is ignoring your hint, it's because it's got a really good reason. And it's something like you've turned on the underscore parameter ignore hints, or you have an invalid hint, or the combination of hints that you have is invalid, or you've misspelled or wrong syntax. So Oracle doesn't ignore hints. So what's going on here? Why isn't Oracle obeying our hint? Well, we tried to reference something in a different query block than what we're using currently. So to show you what I'm talking about, let's use a global hint, right? Before we were using something called a local hint. That means we're hinting something within our local query block. But if we use a global hint, that means we want to reference something in a query block that's not in our current block. In other words, if we want to reference a view, or if we want to reference a subquery or a scalar subquery, maybe a different select and a different union, we would want to use a global hint. So here's how you use a global hint. You say opt_estimate, open parentheses, and then you do an @ query block 1. And you're like, what is query block 1? I'll get to that in just a second. Then you do the keyword table, and then you do your table name, and you do query block 2, and then you specify the number of rows. So this is what a global hint looks like. Query block 1 is the name of the query block after query transformation. Tab is going to be the name or the alias of your table, and QB2 is going to be the query block before transformation. You say, what do you mean query block before, query block after? Whenever you give Oracle a query that has a bunch of query blocks inside, Oracle many times will take these query blocks and merge them together as part of its optimization process using different heuristics. And so if I have query block A and query block B and I merge them together, I can't really call the resulting query block A or B. I have to call it something new. So basically what it does is it takes query block A and B and hashes it and comes up with the end result. So you don't need to worry about all that. The question is, where do you get these values? Where do you get QB1 and QB2? You get those values from dbmsxplan.display and from the format parameter. Whenever you get your plan back using dbmsxplan.display, you pass in a format parameter and you say plus alias. And whenever you do this, Oracle is going to add a brand new section to our explain plan. It says query block name / object alias. And we find the object, the step in the execution plan that we're trying to hint. That's this one. This is the step that has the bad cardinality associated with it. We've only got 5 rows. And down here is the corresponding query block and alias name. We can see that this 1 corresponds with this 1. So that's what we're talking about here, 1 and 1. And we can see that this is our query block 1. This is our query block after transformation. It's that gobbledygook. And this is our query block 2 right here. So all we have to do to use this is add an @ sign right here and throw it into a hint. So instead of using bobs, we're now going to use something that looks like this. It's a little bit different, but it's not a big change. You say opt_estimate, open parentheses. You say @ sign. Then you say the name of the query block right here, comma, the keyword table, comma, Bob's at SEL$2. That was, if we go back, SEL$2 was the name of our query block 2, comma, rows equals 100. So now we've got this going on, and we can see that Oracle, in fact, thinks that there's going to be 100 rows. In spite of the fact that we've got a view, we're able to reach down into the query block where this view is located and tell Oracle, hey, from this operation right here, we should expect 100 rows. So we've talked about like and leading wildcards. Let's talk about outlier values for just a second. Suppose that we have a table that is tracking subscriptions. All right. And that we have the data distributed in such a way that there are 100, let's say that our table has a bunch of columns. We don't care about all the columns. The only column that we really care about is this expiration date column right here. And the expiration date column has 100 rows for each date between January 1st and December 31st, 2009. So in other words, we have 100 rows for that have an expiration date of January 1st, 2019, 100 rows that have an expiration date of January 2nd, 2019, 100 rows that has January 3rd, 2019, all the way down until we get to December 31st. So we've got all these rows. And then let's suppose that we have some subscriptions that are lifetime subscriptions. People have paid for these subscriptions and they're getting lifetime access to whatever it is. There are a couple ways we could do this. For example, we could just have an expiration date of null. Something like that might represent a subscription that never expires. But maybe the architects went, you know what, nulls are tricky, and I don't know if our developers are going to understand nulls, and so we're just going to, instead of using nulls, we're just going to use a date that's way out in the future that we're not going to have to understand or deal with. So instead, we just use the date December 31st of year 9999. So that's 7,000 years into the future, basically. So December 31st of the year 9999. So let's say that we have 100 rows that have this expiration date, 100 lifetime subscriptions. Let's add an index. We'll say create index, subscription index on our subscriptions table on the expiration date column. And then we'll gather statistics to make sure that we're dealing with the most up-to-date statistics possible. If you see cascade equals true, that means that go ahead and gather index statistics. Go ahead and gather statistics on the indexes as well while you're gathering statistics on the table. And then let's ask the question, how many subscriptions will expire in 2019? So we'll do explain plan 4, select star, from subscriptions where the expiration date is between January 1st of 2019 and December 31st of 2019. And if we get this back, Oracle says there's going to be 105 rows. Well, we know that's wrong. I just told you how the table works out. There's 100 rows for every single day between January 1st and December 31st, which means there's going to be 36,500 rows total. So the question is, how did Oracle miscalculate so much? Well, by default, Oracle assumes that if there's no additional help, if you just gather regular statistics, Oracle is going to assume that data is uniformly distributed. In other words, we've got our minimum value, which is January 1st, and our maximum value, which is December 31st, and the data is going to be evenly sprinkled between your minimum and your maximum values. The reality of the situation looks a little bit more like this, and this is not even to scale. We have a lot of data down here in 2019, and then we have this huge gap that exists all the way until we get to December 31st, 9999, and then we've got a few records down here. And it's this huge gap and this uneven distribution that throws everything way off. So how do we fix something like this? Well, one example of fixing this would be using the opt estimate hint. There's another way that we can use this. Before we used it with a table keyword, but you can actually use this with the index scan keyword, and that tells Oracle to correct it on an index scan. There's another way you can use it, and that is through the index filter. So there's two different versions here. We can use either index scan or index filter. And you might be thinking, and it works similar to the other one. You say my tab, that's going to be the name of your table or your alias, and my index is going to be the name of your index. So you would just plug those in right here. Question is, why are there two versions? Well, what's the difference between the two versions? The difference is that index scan tells Oracle that you need to adjust the amount of the index that we're going to be scanning. We're going to be scanning either more or fewer leaf blocks than you think for this particular index. So what we're telling Oracle is we're scanning a larger or smaller percentage of the index than what you think. And as a result, the cost, if we use index scan and we adjust the percentage of the index, the cost of scanning this index is going to go up, because that means we're reading an increased number of blocks inside this index. The other one, index filter, says you have an accurate representation. We are scanning this many records within the index, but we're able to apply filters before we do table access by row ID. So when we jump from our index and we do that table access by row ID after accessing the index, we're actually able to filter out more records as a result. And so either more or fewer records. And so what this means is we can filter out more or fewer index records than what you think before we have to go and touch the table. And if we use the index filter, that means that the cost of scanning the index is going to be the same. So here's our original query. Let's add a hint. We'll say opt estimate index scan, because what we're telling Oracle is we're not scanning this much of the index. We're scanning this much of the index. So we're scanning the majority of the records in this index. We're scanning, 36,500 out of 36,600 records total. So we have to tell Oracle we're going to adjust the size of the index that we're scanning, and subs is our table alias. We say subscriptions index. That was the name of the index that we built earlier, and we tell it we're actually going to pick up 36,500 rows whenever we do this. When we get the plan back, our cardinality still stays the same. Rows is 105. Why didn't our cardinality go up? Our cardinality didn't go up because we got something better than a cardinality change. We got a plan change. We were doing an index range scan before. Remember, that's why we did the index range scan hint. Now we're doing a table access full. Oracle, it's funny how this happens. Oracle says, okay, I'm going to use this index range scan, and whenever I do, I'm going to grab approximately 105 records. And what our hint does is it tells Oracle, no, don't use that index. If you use that index, you're not going to pick up 105 records. You're going to pick up 336,500 records. And Oracle goes, oh my gosh, that's way too many records in this case to use the index for. Oracle goes, instead, I'll use a full table scan. And I'll only use 105 records whenever I scan this table because it goes about calculating things the same way. So here's a case where we've got something better than just a cardinality change. We now have the plan change to be more efficient. But Oracle still has this cardinality misestimate, which if we were being perfectionists, we would want to correct as well. So let's look at a different way of fixing this. Let's talk about other variations of the word the opt estimate. So far, what we've used is we've got opt estimate. We say rows equals something, something, something. And we're telling Oracle, this is the exact number of rows that you should expect. But there are other versions as well. For example, there's a scale rows hint where you can have 2.17. And you're telling Oracle, take whatever estimate it is that you come up with and multiply it by this factor. Suppose that it's off by a factor of 2.17. So we want to, if we think we're getting 100 rows, we would actually be getting 217 rows. Another example is you can set up guardrails. You can tell Oracle, never let your minimum go below this number. Never let your maximum go above this number. So we're telling Oracle to adjust our number of rows to be between minimum and maximum. Let's go ahead and try using the scale rows version of this hint. So Oracle estimated that there's going to be 105 records, but we know the reality is we should expect 36,500 records. So Oracle was off by a scale. If you take 36,500 divided by 105, that's going to be approximately 347.62. So let's go ahead and add another version of the opt estimate hint. Let's use the table keyword since we're now doing a full table scan. And we're going to say subs. That's our, well, I'm missing a table alias here, but that's fine. And we're going to say scale rows 347.62. Oracle's off by a scale of 347.62. When we get the plan back, now Oracle's closer. It says 36,351. We know that the actual number of rows is 36,500. So the question is, why is Oracle still off? Well, the truth is that there were rounding errors both in the initial 105 that Oracle gave us and in the scale ratio that we came up with whenever we divided 365. So there were rounding errors in both of those. So that's why we're seeing a difference of about, 149? But this is close enough. These cardinality estimates do not have to be 100% correct. They just have to be within a certain ballpark. All we're looking for is close enough, and this is certainly close enough. We are like 99% of the way there. So we've talked about like and leading wildcards, and we've talked about outlying values. Let's talk about correlated data. This is cool stuff. And the reason that this is cool stuff is because there are documented fixes for correcting like and leading wildcards. You can use dynamic sampling. You could get creative with the way that you phrase the predicate and cause Oracle to get accurate answers with virtual columns. There's lots of ways of doing that. Outlier values, you can use histograms with. That is a classic textbook histogram case. But when we have correlated data, there's not really a good way to fix something like this with a documented hint. So this is a perfect place. You say, wait a second, Kaylee, I know that's not true. There are things like extended statistics where you can create column groups, and that helps with correlated data. That helps if the correlated data is in the same table, but what if you have correlated data that's in different tables that you have to join together? What if you have join skew as a result of joining this table to that table, and you have data skew within your join? Those kinds of things can't be solved by column groups. So let's give you an example of what I'm talking about. Let's say that we have a table full of actors. So we have, actor, 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 actor. We have 1 million actors in our table. And then we have a table that's full of movies. So we've got a movie, 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 movie. And we've got, 1 million rows in our actors table, 1 million rows in our movies table. Now, in order to represent the relationship that actors and movies have. See, an actor can be in multiple movies, and a movie can star multiple actors. So we would need a junction table between these two tables to represent our many-to-many relationship within our database. So actors table has 1 million records, movies table has 1 million records. Let's say that our junction table has 2 million records. So on average, every actor stars in 2 movies, and every movie stars approximately 2 actors. Let's write a query now. Select star from actors, interjoin the junction table on actor ID, interjoin movies on movie ID, and then we'll say where the actor name is equal to Kevin Bacon, and our movie title contains THE. So it could contain the word the, or it could contain something that, a word that contains the word the, like theater or these or there or whatever. So we have, this is our query. And we have an extremely tight filter on our actors table. We know exactly the actor that we're talking about. We have 1 million actors. We're only talking about one, and that's Kevin Bacon. So we have an extremely strong filter here. Only 1 out of 1 million records is passing our filter. So it's an extremely strong filter. 0.0001% of the records pass our filter. That's a great filter. Then we have an extremely weak filter on the movies table. We're going to say about 1/3 of the movies contain the word the or these or theater or something like that, contain THE in them somewhere. So normally what makes sense to do is to join from your strongest filter, your actors table, and then slowly navigate over to your weaker filter. So actors to junction to movies. If you have 1 row here, and then if we have on average 2 actors per movie, we would join to the junction table, and we would have join uniformity and have 2 rows right here in the junction table, and then that would give us an intermediate result set of about 2 rows. So Oracle takes actors to junction, joins those 2 together, we get 2 rows, and then we use those 2 rows to then join to the movies table, where we would filter out 1/3 of 2 records, which we'll just say that leaves us with 1 record. So our final result set is going to be 1 row. Okay. Usually what does not make sense is going from the movies table over to the junction table to the actors table. If we join in this order, we're going from our weaker filter over to the stronger filter. That usually doesn't make sense. Here's why. We would apply our filter down to 1/3 of our 1 million movies, and we would have 333 million rows. And then if every movie has on average 2 actors, then we would multiply our result set by 2 whenever we join to the junction table. So if we assumed join uniformity, we would have this intermediate result set of 666,666 rows. We would then take our 666,666 rows, join them to the actors table, and we would have 1 row over here. So that would give us a final result set of just 1 row. Okay, so looking at these situations, I've got an intermediate result set of 2 row and 1 row, or I've got an intermediate result set of over 500,000 rows and then 1 row. Which one would you rather deal with? How much data would you rather scan through? You'd much rather scan through just 2 rows and 1 row. So this is going to be usually more efficient in situations where you join from actors junction and get 2 rows. But what if Kevin Bacon acted in all 1 million movies? What if every single movie actor combination in our junction table listed Kevin Bacon and Tom Hanks, Kevin Bacon and Denzel Washington, Kevin Bacon and Brad Pitt, Kevin Bacon and Angelina Jolie, etc.? What if every single movie was just Kevin Bacon and another actor? Well, we would have massive join skew. If we join from the actors to the junction to the movies table, it would look like this. We'd have 1 row here, and then we'd have 1 million rows here due to this huge join skew. So we have this intermediate result set of 1 million rows, and then we would join in the movies table, and we'd filter out about 1/3 of them, and we come up with a final result set of 333,333. If we go the reverse way around this time, we say the movies to the junction to the actors table, we would filter down to 333,000. We would join to the junction table where we'd have 666,000. And then we would apply that to the actors table where we'd filter down to just 1 row. And we'd have a final result set of 33,000. So we come up with the same number of N records both times, 33,333, 33,333, but our intermediate result sets are what are bigger here. We've got 667,000 rows here and 1 million rows here. I would much rather deal with 667,000 rows. So in this case, movie to junction to actors is a better join order. The problem is whenever we do this with Oracle, Oracle is always going to assume join uniformity. So if we issue an explain plan for our query, here's what it looks like. Oracle says, yep, I'm going to first visit the actors table, and we're going to loop around, and I'm going to grab some records on our junction table, pick up 2 records here, and then I'm going to do an index unique scan on the movies table here, and then we're going to do table access on our movies table, and we're going to end up with just 1 row. Oracle assumes, oh, we're just going to deal with 1 row. But if we're actually dealing with 667,000 rows, then Oracle's going to pick the wrong plan. We know that the join order should be opposite. So how do we fix this? We fix it with the opt estimate head. Here's another version that we can play with. We tell Oracle, whenever you join all these tables, you're going to have 99 rows. So table A is going to be the name or the alias of your table. Table B is going to be the name or the alias. You can include as many as you want. Table A, table B, table C, table D, table E, etc. And whenever you do this, if we were to inject a hint like this, here's what it would look like. We would have opt underscore estimate, open parentheses, the keyword join, that's not a placeholder, that's the word JOIN, comma, open parentheses A, because that's our actors table, comma B. If we tell Oracle, when you join the actors to the junction table, you should expect there to be 1 million rows. Now, whenever we do this, you can see, okay, Oracle goes, yeah, actors to the junctions table, I'm now going to have 1 million rows. So that's 1,000 K. That K represents an additional 1,000. So that's 1,000, that's 1 million. Or I don't know why Oracle didn't do it, just go 1 million, but it did. But we still have a little bit of a cardinality misestimate right here on the movies table. So all we would have to do is just apply an additional filter on the movies table. So that's going to be opt estimate, open parentheses, table. C, we'll say rows. We're going to get approximately 333,000 rows for the table. And if you look, now Oracle is no longer using nested loops. It's now using hash joins, and the join order is the exact opposite of what it was. The first thing that we do is we talk to the movies table, and then we join that up with the junction table, and then we take the result of that and join it up with the actors table. You can see that the movies expects 333,000 rows. The hash join expects about 665 rows, 665,000 rows, and our actors table only has 1 row. So there's lots of variations of this very useful hint. You can have one for table, index scan, index skip scan, index filter, join nested loops, index scan, nested loops, index filter, group by, query blocks. There's all kinds of ways that you can use this. And there are variations of how to rows. I think we talked about all these. Rows equals 99, scale rows, min rows, max rows, or you can combine scale rows with min and max, or just one or the other. It doesn't really make sense to say rows and then min, or rows and then max. So you wouldn't necessarily want to do that. But if you're using scale rows, then absolutely, it might make sense to combine these. So this is the point where I've got a little bit of time for QA. I don't know, do people type in their questions here? Is that how it works? That's how I'm used to doing it. Usually people are typing in questions and there's a short little lull.
That's right, Kaylee. People generally type in the question.
Okay. So while you're typing in your question, just to avoid any kind of awkward lull, I'm going to actually ask myself the first question. So if you got a question, start typing it in. I'm going to ask the first question. I talked about how accurate is close enough. Usually the answer is you want it to be roughly within the same order of magnitude. So if you have an estimate for 30,000 and your actual number of rows is 90,000, that's probably close enough. Okay. But if you have an estimate of 30,000 and your actual is 300,000, okay, well, maybe it's time to adjust the cardinality. If there are any, here's another question is, if there are multiple cardinality misestimates, which should I go after first? You want to go after the first and the earliest possible in the join order, because if you fix earlier cardinality misestimates, those might cascade to fix later cardinality misestimates. I'm getting some things in the chat here. How do we change the constant hash plan changes? How do we change constant hash plan changes in the database for SQL IDs. Alter system set. Hash plan changes. I'll shoot straight with you here. I don't know what you're talking about when you say hash plan changes. There's a plan hash. Okay. So if you're just concerned the plan hash. Okay, so the plan hash. Okay, that's okay. Okay, I see what you're saying. You're wanting to know how to prevent the plan from changing. Okay. Adaptive features, that would be one way, but honestly, I would refrain from disabling optimizer adaptive features. First of all, there's a lot to unpack there. Optimizer adaptive features is an old version of the parameter. That's for 12.1. Whenever you upgrade to 12.2, there's actually a something that will split those into two different parameters. One that talks about adaptive joins, and the other one talks about adaptive statistics. Most people have trouble with adaptive statistics. Adaptive join works really well, but there's actually a patch to backport the splitting of this optimizer adaptive features into those two different parameters. So I would work on, first of all, installing that patch. If the optimizer adaptive statistics is giving you a headache, then certainly, disabling it until you can get that patch installed is one way, but that's not going to necessarily be enough to totally prevent all plan changes ever. And that's not necessarily what you want either. To some degree, you do want things to be adaptive, especially if you're using bind variables, but there's other things as well, such as adaptive cursor sharing, that's going to be looking at, if you're using bind variables on histograms, those are going to do things like change your plans. So, if you wanted to, you could baseline everything. You could create a baseline for every single SQL statement. And that would give you that would freeze your plan. That's what a baseline does. I would be hesitant to do that, especially if the query is just not giving you grief. If the query is not giving you grief, then I would leave it alone. For those queries that are giving you grief, you could use a baseline to optimize those. But the adaptive join stuff actually works extremely well. The hash joins to nested loops, that's something that I've not heard a lot of people complain about. Now, the adaptive statistics with the adaptive dynamic sampling, and those can definitely cause some people some grief, so I definitely understand that. What are some other hints that work well in conjunction with what are other hints that work well in conjunction with opt estimate? So literally anything that you want within an execution plan, within reason, you can pretty much hint a behavior to get that particular step if it's within reason. I can't just throw if I have a table, if I have a query that doesn't have any aggregation, I can't suddenly create a hint that forces Oracle to do a hash group by or something like that. But there is a crap ton of hints, and literally there's hints for specifying your join methods, specifying your access methods, how you're going to use indexes, how you're going to do full table scans methods, what order you should join the tables in. There's a leading hint and an ordered hint. Both of those are going to control your order. Things such as whether you should unnest. So there's a crap ton of hints. That's just something that you kind of have to, I guess you kind of have to research. So that's pretty much all I have there. Creating and enabling a baseline is good or not good for a SQL ID after pushing best plan hash value both by SQL Tuning Advisor if push manually also. It depends, okay? So it could be the best if you always want the exact same plan, but there are times when you're not going to want the exact same plan. There are times when you might feed one bind variable to your plan that selects a large volume, and there might be other times whenever it selects a small volume. So that's something that you want to keep into consideration, that sometimes you want these plans to be adaptive, but I don't reach for a baseline unless something is broken. If the SQL Tuning Advisor gives you some advice, maybe it's going to create a missing index for you or something like that, that might be enough to fix your issue. I kind of would say don't fix what isn't broken. If the SQL tuning advisor says, please create this index, and you create the index and it doesn't give you any more grief, then it might be a good idea just to leave well enough alone. So that's my thoughts. What other questions do we have, if any? I've got some more time filler. I wasn't expecting, you guys are ambitious. That's good. Wasn't expecting so many questions so quickly. I'll ask a couple more in case there's any more. If you got questions, type them in. How do I find actual versus estimate cardinalities? This is something that a lot of people ask. You can use something called extended row source statistics. You can do an alter session, set statistics level equals all, and that'll turn it on. Or there's a hint that you can use called gather plan statistics. And if you do this, whenever you select from a table, DBMS explain.display cursor, you do all stats last. Then Oracle will show you two new columns. It'll show you this is the number of rows that I expected for this operation, the expected rows, the E rows. And this is the actual number of rows that I got. So this is the actual number of rows that I got from this execution. Another place you can look is a SQL Monitor Report. This is the estimated number of rows here, and then you've got the rows. It's not labeled actual number of rows, but this is just the actual number of rows. So if it says rows, it's the actual number of rows. If it says estimated rows, it's just an estimate. I've got more questions here. Are there any discussions, blog forums where we can discuss and interact with you where you actively share ideas? Yes, there are. I have a SQL tuning group that you can join. It is tuningsql.com/group. If you go to that group, you can join. And I throw some content out there every once in a while. It's just getting started, but that is, I can just type that in here, tuningsql.com/group. Blogs, I've also got a blog, blog.tuningsql.com. Oop, I need a little dot there, blog.tuningsql.com. Wonderful session, thanks a lot. Good insight on Optus estimate, thank you so much, you're kind. My question may not be related to the session. What is a better SQL tuning approach if developers written through 400 or 500 lines of code with hundreds of union all? Okay, so if this query is not performing very well for you, then you want to do something called time analysis. And that is, you want to look at which sections of the query are causing your are being your bottleneck. And you can do this through a number of ways. One way to do it is if you have the tuning and diagnostic pack, you can get a SQL Monitor Report, and that will show you which steps are taking the longest. If you don't have the tuning and diagnostic pack, then you simply want to use tracing. And you would create a 10046 trace file, and then you would throw that to tkprof, and tkprof will show you that each step takes approximately this amount of time. And the way that it works is the sub-step is calculated in with its parent step. So if I have a hash join that takes no, let me say this differently. Let's say I have a filter step and it says, well, this takes 13 seconds. And then I have a table underneath, a table scan, a table access full underneath, and it takes 12 seconds. What that really means is the table scan took 12 seconds and the filter step took, what do they say, 13 seconds? So that'd be 1 second difference between the two. So your filter only took one second and your table scan took 12 of those seconds. So you would want to look at that. So those are my blogs and my other things. I'll just do one last thing here. Why do tables join in nested loops seem to always estimate just one row? If you look here, you see this has got one row. What this means, Oracle has wired this weird, where if you do a full table scan and you do nested loops, on this second table for a nested loops child, this estimate means for each iteration of nested loops, I'm going to pick up this number of rows. So what Oracle is saying is, I'm going to pick 10 rows up here, then I'm going to do nested loops, bubble down to this operation, and I'm only going to pick up one row for each iteration, but I'm going to loop through this 10 times because I picked up 10 rows. So 10 rows, 10 operations through this nested loops. I'm going to pick up 10 rows here and then pass those up to the nested loops here and do 10 rows here. And I'm going to have 10 rows total. So the way that nested loops are configured is just a little bit different. Let's see. For example, a SQL query got executed 100 times, and then they see slowness sometime among that, not all times. How do we find which execution is slow and what causing 100 times? We can see the average time and average ID, but no option to check each execution, right? Is there any tips? Okay. Hopefully you have the tuning and diagnostic pack. And if you do, then you would want to look at active session history. There is a view called $v active session history. And that basically is going to record, that records a lot of things. That records for every active session that you have, that's going to record every 1 second, it's going to record a sample of that. It's going to record things such as what step of your execution plan are you on. It's going to record things like your wait events and your CPU utilization. So this is, if you have active session history, the tuning and diagnostic pack, you can query the $v active session history table, and that will give you historical information as far as what's happened in the past. Now, the bad news is you want to catch this pretty early if you can, because this table by default tends to get wiped out after about an hour. So if you do run into an incident, you have somebody complaining, the first thing that you want to do is just do like a create table whatever as select star from $v active session history. That will give you a wealth of information of things that have happened over the past hour, and you can use that to look at which individual SQL execution, which individual plans have caused you the most grief, and you can go find those plans within your $v SQL view, and you can use those to hone in on which individual SQL statements that you're looking for. Another question. Cast function versus proper index creation will make a difference for a same query. Cast function versus proper index creation. Okay, I'm not 100%. Are you talking about like function-based indexes versus non-function-based indexes, like a function-based index that might use the cast function and a non-function-based index that might use the same thing? Is that what we're talking about? Yes. Okay. Here's the deal. You talk about proper index creation. That's what you want to do, and here's why. You want to have the fewest number of indexes possible on your tables, because for every index that you add, anytime you do a change to the table, for every insert that you have to do, you're not only inserting into the table, you also have to do a subsequent insert onto the index. If you're doing an update on the table, or if you're doing a delete on the table, you have to delete from the index. If you're doing an update on the table, if you're updating an index column, you have to delete out of the index and then reinsert into it. So you want to have as few number of indexes as possible. So I like to avoid function-based indexes, because function-based indexes tend to be geared towards a specific query. Whereas if you can just index the regular column, then that's going to allow you to have fewer indexes. You're going to have fewer indexes, and they're going to be more generic. They're going to serve a greater number of queries. So that's the real reason that I would recommend. As far as efficiency versus how, what data is being stored and is there any difference in how fast, I would not expect there to be a significant difference on a function-based index versus a regular non-function-based index. But the real reason that you want to index your queries in a certain way is so that you can avoid being in the trap of making a specific index for this query and then making a specific index for that query, making a specific index for the other. You don't want 100 indexes on one table. You just want 2 or 3 most, if you can help it, right? You might have 15 foreign keys on the table, and each one of them have to be indexed. That's totally fine. But you want to have the fewest number of indexes possible. If the query is not using an index, how to force it to use an index? Well, there are a number of hints. There's an index hint that you can do, and I don't remember the exact syntax, but I'm more than certain that it's out there in the Oracle documentation. There are specific kinds of hints, such as index range scan ascending, index underscore. So there's an index underscore rs underscore ASC hint. That's for an index range range scan ascending. There's a conversely an index range scan descending. There are hints for index fast full scans. There are hints for index skip scans. If you just look at Oracle hints and type in, whenever you get to that page, you type in find and type in the word index, you're just going to see a crap ton of stuff as far as how to hint certain behaviors within indexes. How do you discover the undocumented features? I've had this question a lot. It comes from a variety of things. It comes from looking at blogs, looking at some of the underlying tables in my own database, logging in assists, and looking at some of the the X dollar views and stuff. Some of it, yeah. I mean, you can find books out there, entire books on just undocumented Oracle features. The real thing that I wanted to give away is this. An 11-page document on the opt index hint, everything that we talked about today. If you go to tuningsql.com/undocumented, you can have an 11-page document on the secrets for getting accurate cardinalities, and you can get the slides. A lot of people ask me for the slides for this presentation. You can get all that information at tuningsql.com/undocumented. If you do that, you'll also get on my email list where I send you free SQL tuning tips. I don't spam you. I don't rent the address or anything like that. I just send you free SQL tuning content. So this is one place you can go, SQLtuning.com undocumented. You can also go to my Facebook group, tuningsql.com/group. And, we got something else here. Suppose if an index is created on a table for 3 columns like A, B, and C, we're querying the table by end user and querying that table by end user like B, C, A order. At the time, it shows index range scan only, but performance is slow. At the same time, it shows index range scan only, but the performance is slow. Whether we need to ask the user to rewrite the query in the same order as the index creation. Any tips on that? So if you have equality predicates, then it doesn't necessarily matter which order, if that makes sense. So if I've got select star from some table where column A equals A and column C equals C and column B equals B. If I've got a query that looks like this, and I've got A, C, and B, but my index is maybe on A, B, and C, the order of these does not matter if they are equality predicates. So it doesn't matter. You don't have to rewrite a query to match index order if that's what you're talking about. If they're not equality, if you have like a between or greater than, then you want to make sure that your equals are indexed first, and then anything with like a between or a greater than or equal to or less than or equal to or greater than or less than, you want to put those at the tail end of the index. This is actually a concept that's covered in my free SQL tuning guide that you can get at tuningsql.com/secrets. You can get, that is my free guide that you can go get. That is 7 SQL tuning secrets that you can use even if you've never tuned a query in your life. You can go grab those, and you might think, oh, it's all beginner stuff. Some of it is beginner stuff, and some of it is this is what I use whenever I get called into a paid performance gig. So it's not to be sniffed at just because you're like, oh, well, that's beginner stuff. No, this is the stuff that I use for actual performance tuning gigs that I use. You can go get my secrets at tuningsql.com/secrets. So lots of content to give you guys. Yeah. Sorry, I have been just motor mouthing, and we are encroaching. We're coming up on 9:30. I'm not trying to.
Right. I know in respect of time, if there is anything else, maybe you could get into the group of tuningsql.com and then connect with Kaylee for that. We will now if there is anything else that you want to convey, Kaylee, you can do that. Otherwise, we are good to wrap up the session.
I'm good. Thank you so much for having me. I appreciate you guys.
Very good. Thanks for a great session. It was a lot of insight in terms of tuning. We were over 100 participants and we had few more connecting via Facebook Live. So
Wow.
it was very interactive as well. Thanks for your time. And I'm sure there's going to be a lot of people who will come and join us in your group and will benefit more from this. Thanks, everyone. And be safe and have a nice day. Bye.
Thanks, guys. Take care.
Thank you, Kelly. Bye.